Welcome to the video lecture on exponential functions. In this lecture, we're going to begin studying one of two very important functions in mathematics, the exponential function. And in a future lecture, you're going to learn about its inverse called the logarithmic function. These functions can help us model a wide variety of natural phenomena ranging from growth patterns in populations to the value of money to radioactive decay, learning curves, the spread of a virus or a rumor, carbon dating, and a host of other situations. So there's a lot of applications that surround exponential and logarithmic functions. Let's first start by looking at the exponential function, and by definition we say that an exponential function has the form f of x equals a to the x, where a is your base, it's a constant base, and the variable is up in this power x. We say that the base a is greater than 0, so you want to only have bases that are positive, and we let x be any rational number. So there's two situations that can arise here. If your base a is larger than 1, then what we're going to see happening is something called exponential growth. And this would be the type of graph that starts off close to 0 and then rises up very rapidly as we progress to the right. And this is going to be for anything of the form a to the x where that base a is larger than 1. So something like 2 to the x, 3 to the x, 4 to the x, and so on. In the opposite direction, we have what's called exponential decay, and that's going to be this same graph reflected over the y-axis. So this would start off really high, but then it's going to decay to 0 as we progress to the right, so as x goes towards infinity. And this happens whenever your base a is between 0 and 1, and that implies that your base a is a fraction. So let's see how we would actually get these shapes, these growth and decay graphs. So we're going to start with a very basic function, f of x equals 2 to the x. So this is an exponential function that has a base of 2. Since that's bigger than 1, we would expect to see a growth type shape. But if you didn't have any idea how to graph it, then the only place to start is with a table. So we're going to make a table of x and y values where our y values are coming from this formula 2 to the x. And if you don't know what x's to use, then just take a nice selection of x's. So I'm going to use -2, -1, 0, 1, and 2. And we're going to plug in these negative exponents into this power up here. So this would become 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the 2. Now when we go to simplify these, remember that negative exponents flip over or take the reciprocal of your expression. So 2 to the -2 becomes 1 over 2 to the +2. And if we simplify that, 2 squared is 4, so this becomes 1/4. If we plug in a -1 power, that's the same as flipping this over and making it 1 over 2 to the 1st, and that just is 1/2. 2 to the 0, anything to the 0 power becomes 1. 2 to the 1st stays 2, and 2 squared becomes 4. So if we plot these points, we're going to get -2, 1/4, so really small. -1, 1/2, so still small but just a little bit higher than the last point. 0, 1, so it goes through 1 on the y-axis, that's your y-intercept. 1, 2, and 2, 4. Now, as this power gets more and more positive, imagine what's going to happen. So if I were to make this 3, 4, 5, and so on, then this would be 2 cubed, 2 to the 4th, 2 to the 5th, and these numbers are just going to keep growing. 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. So these y values are going to continue to get higher and higher, faster and faster. So this graph is going to continue to grow as we go to the right. Now let's look in the opposite direction. As this input here becomes more and more negative, that makes this power more and more negative. Because it's negative, it flips it over, and this power in the denominator then gets larger and larger. So for example, 2 to the -3 would become 1 over 2 cubed, which would become 1/8. what's happening to these fractions as this power becomes more negative? Well, the more negative this number gets, the larger this power in the bottom becomes, so the larger this denominator becomes. And 1 over something large is going to get small. So that's why these points on the left continue to shrink down lower and lower and lower. But is this ever going to hit 0? Can 1 over a number ever actually equal to 0? No. It's going to get really close to it, but it's never going to actually hit 0. So there's this imaginary dashed line right here that represents our horizontal asymptote at the height y equals 0. Okay, so this is how we get our graph of 2 to the x. Now let's do a similar graph, but this time I'm going to change my base to a 1/2. So this is going to be 1/2 raised to the x. And if I want to get the graph of this, again, I'm going to make my table of values. And in the last problem, I did -2 all the way up to 2. Most of the time, it's sufficient to just go from -1, 0, and 1 and use those 3 inputs. Most of the time, those 3 points will be enough to give you a feel for what the graph should look like so that you can draw a rough sketch. If you're ever unsure and you don't think that this is enough, you can always plot additional points, but you want to have at least these 3. So let's plug in -1, and this would become 1/2 to the -1. Plug in 0, so this becomes 1/2 to the 0, and if I plug in 1, it becomes 1/2 to the 1. Now remember, those negative exponents flip you over. So since this is a fraction already, when I flip over that fraction, this would become 2 over 1 raised to the positive 1, and 2 over 1 is 2, 2 to the first stays 2. For the second input, 1/2 to the 0, anything to the 0 stays 1 or becomes 1, and 1/2 to the 1 stays 1/2. So this is going to be -1, 2, 0, 1, just like the last equation, we had a y-intercept of 1, and here we do as well, and then 1, 1/2. So again, you can imagine that the more negative this number gets, it's going to flip over our fraction, and it's going to make this power up here get bigger and bigger and bigger, which is going to make this number over here get larger and larger. So as I go to the negatives to the left, this is going to continue to grow. As I make this power larger and more positive, then this is going to make this fraction get bigger and bigger and bigger in the denominator. So for example, 1/2 squared if I used 2, 1/2 to the third if I used 3, and 1/2 squared is just 1 over 2 squared, which is 1/4, and 1 over 2 cubed, which is 1/8. So the larger these x's become here, the larger the power becomes in the denominator, so the larger the denominator gets, which makes the fraction overall get smaller. So these numbers are going to continue to shrink as they go to the right, and we will see that dashed horizontal line again at y equals 0. So let's summarize our characteristics of these exponential functions. First of all, and we saw this in the last 2 examples, every exponential function a to the x will contain the point 0, 1. And that's because a to the 0 equals to 1. So this is assuming a very basic exponential function. There's no shifts or reflections or any kind of transformations that have been applied to this. So all of these characteristics that I'm talking about apply to the very basic a to the x graph. So every a to the x graph will go through 0, 1. It will also go through 1, a, because a to the first is a. And it will also go through -1, 1 over a, because a to the -1 gives you 1 over a back. You'll also notice, and we talked about this already, that when that base a is greater than 1, the graph increases, and we get that exponential growth shape. When the base a is between 0 and 1, or in other words, a fraction, then the graph decreases, and we get that decay shape. You'll notice that when the base is greater than 1, where is this graph acting asymptotically? It's being asymptotic over here on the left side. So as x goes towards those minus infinity numbers, the y values go to 0. When the base is a fraction between 0 and 1, then the graph is asymptotic over here on the right. So as x goes to positive infinity, these y values go to 0. What's the domain of both of these graphs? Well, the domain is always all reals. You can plug in any x value you want, and you'll always have something that exists. What's the range of these graphs? No matter what base you have, both of these are asymptotic to y equals 0. So they never actually hit 0, and all these y values are positive. So our range is 0 to infinity, not including the 0. Also, the function is 1 to 1. Remember that horizontal line test that we use to check to see if something is 1 to 1? Both of these graphs pass the horizontal line test. So if it's 1 to 1, that means it has to have an inverse function, which is important because if it has an inverse function, we're going to have to be able to find it, and what it's called happens to be the logarithmic function. And then finally, all the transformations that we've applied to other kinds of graphs, like quadratics, absolute values, square roots, all of those same transformations apply to the graph of an exponential function. So we're going to talk next about how you shift these graphs, how you reflect them, how you compress and stretch them. So let's take a look at this first example. We want to sketch the graph of the following function and also indicate the transformations that are being applied. So if we have 3 to the x minus 1 plus 2, this is essentially the graph of 3 to the x, but we have this minus 1 and we have this plus 2 on the side. So what does the minus 1 up here next to that x do to our graph? Whenever your plus or your minus is next to the x, that's a horizontal shift. Remember, horizontal shifts are backwards from what you would expect. So minus 1, we probably think go left, but we're actually going to go right. So this is going to be a shift right 1. And then the plus 2 is off to the side, away from that 3 to the x function. So that makes it a vertical shift, and these go in the direction that you would expect. So when you see a plus 2, that means this is going to go up 2. So we're shifting right 1, and we're shifting up 2. Now think about that up 2 for a moment, because that's really important. Normally our graph has a horizontal asymptote at a height of y equals 0. If we are shifting this entire graph up 2 units, any kind of vertical shift up or down is going to affect the placement of that horizontal asymptote. So if we're shifting up 2, that means we are going to have a new horizontal asymptote, no longer at 0, now it's going to be at a height of 2. And I like to show that by putting in that dashed horizontal line right away, because again, it reinforces the fact that I should not be graphing below that line. Okay? It helps keep me in the right place when I'm graphing my exponential function. Now, to get the actual graph here, what you're going to want to do is make a table of values. You're always safe making a table, and I'm going to use this rule, 3 to the x minus 1 plus 2. And it's always safe to start off with -1, 0, and 1. And you can modify that if you like, and we will do so in just a moment. But your first initial attempt here at graphing, it's always sufficient to just use the 3 inputs, -1, 0, and 1, and then go from there. So let's plug in -1 for this little x up here. Now you do need to be careful with your order of operations here. We need to simplify this power first, so this becomes 3 to the -2. Then we need to do our exponent. 3 to the -2 is like 1 over 3 squared, which is 1/9. And 1/9 plus 2, 1/9 plus 2 is 2 1/9. Okay, and you can get decimals if you want, but I'm just going to leave it as a fraction. Now let's plug in 0 for that x. So I'm going to plug in 0 up there in that exponent. Simplify the exponent first. So 0 minus 1 is negative 1. Simplify this exponent right here. 3 to the negative 1 becomes 1 over 3 to the positive 1, which is a third. And a third plus 2 is 2 1/3. And then if I plug in 1 for that exponent x, 1 minus 1 is 0, 3 to the 0 is 1, and 1 plus 2 gives me 3. Now it's certainly fine to use just these 3 points and plot those. Sometimes what I'll do is I'll take into account my horizontal shift when I'm making my x's and my choice for my inputs. Remember that normally we would use negative 1, 0, and 1, but this graph had a shift right of 1. So sometimes what I'll do is I'll shift my inputs right 1 as well. So instead of stopping at 1, I might shift that right 1 and boost it up by 1 and look at what happens when x is 2 as well. You don't have to do that, but sometimes it gives you a nicer range of y values to plot so that they're not all scrunched together and hard to differentiate between. So let's plug in 2 as well for our x, and let's see what we get. 2 minus 1 is 1, 3 to the first is 3, and 3 plus 2 is 5. So the nice thing about using this 2 is now your y's aren't quite as scrunched. If I had used just these two x values or y values here, 2 to the 1/9 and 2 to the 1/3 are so close together on my little tiny graph over here that it's going to be hard to tell them apart. But 3 and 5 are definitely a good distance apart from each other, so I'm going to get better points to plot. So let's go ahead and graph all 4 points. Negative 1, 2 and 1/9. All I know is that that's just a little bit bigger than that horizontal asymptote at a height of 2. 0, 2 and 1/3 is just going to be a tiny bit higher than that last point. 1, 3 would be here, and 2, 5 puts me up here. So by adding in that extra x value, by shifting right 1 and looking at 1x to the right, we are getting a nicer distance between these points, and it's easier to see that these are the points that are rising up as I go to the right, and then the points on the left are the ones that are skimming that horizontal asymptote. So there's my graph. Okay, let's try another one. So here we have negative 2 to the 2 minus x minus 3. Now in this one you need to be very, very careful before you start describing or listing what your transformations are. And the big mistake that is often made on these kinds of problems is forgetting to put this into the proper factored form. And the reason I know that I need to do that is if you look at this x up here, it has a coefficient that is not a 1. It has a coefficient of negative 1. So that means I need to factor this expression right here to get it into the proper form so that I can identify correctly what kinds of transformations I actually have. So here's what it would look like factored. I'm going to leave the negative out front of that 2, and all I'm factoring is right here, and what I'm factoring out is that negative in front of that exponent. You can think of 2 minus x as negative x plus 2, and what I'm doing is factoring out that negative in front of the x, and what that would have to leave me with is a minus 2 in parentheses, so that if I were to redistribute, I would get back negative x plus 2. So in other words, in factored form, this is going to be minus 2 raised to the negative parentheses x minus 2, and then that minus 3 on the side. So why do we bother doing all of that? Because then we see that there's a reflection due to this negative, there's a reflection due to this negative, there's a shift due to that minus 2, and there's a shift due to this minus 3. So we're going to be able to clearly identify what all of our transformations are. Now what kind of a reflection is it when the negative is outside of your function, in front of that base of 2. Well, that's when you have a reflection over the x-axis in the vertical direction, upside down. So this is going to flip our graph upside down. When the negative is up next to that x, that's a reflection in the horizontal direction. So this is going to be a reflection over the y-axis. This -2 is also next to that x, so that's a shift in the horizontal direction, and it's backwards from what you would expect. So if I see a -2, I'm actually going to go right 2. And then the -3 off to the side is outside of our function, so that's a vertical shift, and because it's negative, we're going to go down 3. So we have 4 different kinds of transformations going on here. Now, to get a feel for our graph, let's go ahead and make a table. And I'm going to use my rule up here, -2, and you can use either the factored rule or the original rule when you're plugging in your x's. It doesn't matter for that purpose. Okay, so in our table of values, again, you can always use -1, 0, and 1 as your inputs, but sometimes it's nice to factor in or use or take into consideration any sort of horizontal shifts that you have. And since we have a shift right of 2, then sometimes what I'll do is I'll take my last x value here of 1 and I'll shift that right 2 as well. So I might go all the way up to 3 so that I can get, again, a better distribution of points. So let's try these 5 values, and I'm going to plug them in to my function up here. So let's start with -1. Using order of operations, we get a minus minus, so this becomes plus. So we get -2 to the third minus 3. And be careful here, there's no parentheses, so 2 cubed becomes 8, but it's negative, and -8 minus 3 gives me -11. Now let's plug in 0. So -2 raised to the 2 minus 0 minus 3, so I get -2 squared. No parentheses, so 2 squared is 4, but it's going to stay negative, and -4 minus 3 is -7. If I plug in 1, 2 minus 1 is going to be 1, so -2 to the first minus 3 gives me -2 minus 3, or -5. If I plug in 2, 2 minus 2 is 0. Anything to the 0 is 1, but there's that negative in front, so keep that negative. It's going to be a -1 minus a 3, which is -4. And finally, if I plug in my 3, 2 minus 3 would be -1. 2 to the -1 becomes a half, but it's negative. And -1/2 minus a 3, they're both negative, so we're really adding here. So this is -3.5. So you don't have to do all 5 of these points. At the very least, you should do these first 3. But again, it's nice to kind of get a little range of values. Especially some of these other points up at the top of my list get a little large, and that might boost you off your graph. So if you're looking to find some points that fit on your grid a little bit better, it's nice to consider that horizontal shift. Now, before we graph here, one thing we haven't talked about is where should this, or where would we expect the horizontal asymptote to be? And because we have a shift down 3, which is a vertical shift, that's going to take our whole graph and move it up or down. And in this case, we're shifting it down 3. So if normally the horizontal asymptote would be at 0, now the horizontal asymptote is going to get moved down 3, so it would be at y equals -3. So it's nice to kind of know that ahead of time so you can sketch in that graph and make sure that you don't cross it. So let's go ahead and plot our points. We have -1, -11. So that's going to be off my graph just a little bit down here. 0, -7. 1, -5. 2 comma negative 4, and 3 comma negative 3.5, so just a little bit below that horizontal asymptote. And you can see these points are going down as we go to the left, and they're going to start to level off from below towards that horizontal asymptote. So there's the graph of our exponential function. Okay, the next example here is a little bit different. It says find the equation of the exponential function of the form f of x equals ca to the x that passes through the points negative 1 comma 15 and 0 comma 5. So which exponential function has to pass through these 2 points if it's of the form a constant times a to the x? That's what we want to try to figure out. So we're trying to figure out what this constant c should be and what this constant a, or this base a, needs to be. So what we're going to do is basically use these 2 points to help us figure out what c is and what a is. And these points have x's and y's. So we're going to let x be negative 1, and we're going to let y be 15, then we're going to let x be 0, and we're going to let y be 5. So let's go ahead and do that. So for the point negative 1 comma 15, the x value is negative 1, so that's going to go up here in this power right here. So on the right hand side we would get c a to the negative 1, and the y is your f of x, so the 15 is going to go on the left side. For the other point we have 0 comma 5, we're going to let x be 0, so I'm going to put a 0 up where that x is. So we would get ca to the 0, and our y value is 5, so I'm going to put 5 on the left side where that f of x should go. Now out of these 2 equations, this one on the right should look simpler to deal with because a to the 0 simplifies to just a 1. So this part goes to 1, leaving me just c, which means we now know the value of c. That's half of our answer right there. And if we know c, then we can plug that c value in over here and change this equation so that instead of having 2 variables, now it's only going to have 1. So how do we solve 15 equals 5a to the negative 1? Well, the first thing that I would do is divide both sides by 5. Try to simplify that variable part as much as you can. And a to the negative 1 is going to equal 3 when? How would you undo this negative 1 power? Well, there's several ways to do it. You could make it a reciprocal and change it to a 1 over a, and then work out the problem by multiplying by your common denominator. Another option here is if you want to undo a negative 1 power, we can raise both sides to the negative 1 power. And that's because negative 1 times negative 1, we multiply powers when it's a power to a power, this right-hand side just becomes a to the first, or just a. But what does the left side become? What is 3 to the negative 1? It becomes 1/3. So the value of a must be 1/3. So what does our final function look like? Let's plug everything in. The c value was 5, and then that was getting multiplied by my base a, which was 1/3, and I was raising that base a to my x power. So my function is 5 times 1/3 raised to the x. Now we stated that any positive number can be used as the base in the exponential function. Bases 2 and 10 are convenient bases for many applications involving exponential functions, but the most important base of the exponential function is the number e. The letter e is in recognition of a famous European mathematician of the 17th century, Leonhard Euler. The letter e is defined to be the value of the expression 1 plus 1 over n raised to the n as n goes to infinity. E is an irrational number. It's just like pi. It never repeats, and it doesn't have a pattern, and it occurs so often in so many different applications, especially in calculus and above. That's why it got assigned its own letter name, just like pi. So you will see e quite often as you progress through mathematics. Now we said that e was defined to be the value that this expression goes towards as n gets bigger and bigger and bigger. So I want to show you what this becomes. So I'm going to pull out my calculator. Let me move it over here just a little bit. And I'm going to show you how to find out what these values are as n gets bigger and bigger, and I'm going to do it using lists. So what you're going to do on your calculator is you're going to go to this stat button, and you're just going to click on stat, and we're going to create two lists. So I'm going to edit them, which is this option number 1. So either hit 1 or hit enter. And I've done a little bit of prep work here already. I cleared out my lists, and in list 1 I'm creating a list of inputs. These are going to be my n values over here. So I'm going to let n be 1, then I'm going to let n be 10, then I'm going to let n be 100, 1,000, 100,000, and then 10 to the 8th. So basically, let me go back to my screen over here. What I'm really doing is making a table for what this is going to look like, where n takes on all of these different powers of 10. Okay, so this is what we're doing, and now we want to figure out what these y values are over here. So a clever way to do that on your calculator is to go all the way up to your header where L2 is. Make sure that that little L2 is highlighted or colored in black like mine is, and hit enter so that your cursor is flashing down at the bottom. This is where we're going to type in our formula. Now I don't really want to type in 1 plus 1 over, 1 plus 1 over n raised to the n, because the calculator doesn't know what n is. What is n? N is supposed to be all these numbers that I have in list 1. So what I'm going to do is type in this formula over here, but instead of using n for my variable, I'm going to use list 1 as my variable. So I'm going to type in parentheses 1 plus 1 divided by, and instead of n, I'm going to type in L1, because that's where I want the calculator to get the numbers from. Now L1 is in blue right above the number 1 on your calculator, so you need to hit second 1, and you'll see that L1 show up. Then we want to close the parentheses, and we want to raise that to the n power, or in this case the L1 power again. So I'm going to do second 1, and so this looks like exactly the same formula that we want over here, but instead of using n, I'm using L1, since that's where my n values are stored. Hit enter, and in this list over here are all these y values. So we have 2, 2.5937, and so on. Now the bigger this n value gets, look at what these y values are doing. They're starting to approximate a value. This last value here is 2.7183, and it's actually the same as the value right above it. So this expression is approximating 2.718. Okay? So if you take this 1 plus 1 over n raised to the n, as n goes to infinity, this is going to approach approximately 2.718, and if we had more accuracy or more decimal digits that we could show on our calculator, you'd actually see that it goes to 2.71828 ... And this goes on and on forever, and it never repeats, and it never has a pattern. So this is E. So E is approximately 2.718. Okay? So that's how E is defined, and what we're going to see are several different graphing problems and application problems with a reference to this base of E. So the natural exponential function is the function f of x equals e to the x. So whenever you hear the phrase natural exponential function, you know that that's implying e, base E. Sometimes we get lazy and we don't even say that word natural, and we just say the exponential function, and if we say that again, we're implying that base E. Because e is about 2.7, which is between 2 and 3, then the graph of e to the x lies between the graph of 2 to the x and 3 to the x. And that's because e is between 2 and 3. So let's see a couple of graphical examples using this base e. It's not going to be any different than what we were just doing. The only difference is that because e is this yucky decimal, our table values are probably going to be a little messier than they were before when we had nicer bases. Okay? So let's take a look at e to the negative x plus 1. And we're going to graph this, and we're also going to make note of any transformations that are happening. So if I have e to the negative x plus 1, I see a negative up here, and I see a plus 1 over here. This negative is up next to that x. So anytime you're next to the x, that's a horizontal transformation, and because it's a negative, that's a reflection in the horizontal direction, which means it's a reflection over the y-axis. Okay? And then the plus 1 is away from that x, off to the side, so that's a vertical shift, and because it's plus 1, this is going to be up 1. And you should already know that because we have a vertical shift here, anytime we're shifting up or down, that's also going to shift our horizontal asymptote as well. So instead of having a horizontal asymptote at 0, we are going to have a horizontal asymptote at a height of 1. So you can go ahead and sketch in that dashed horizontal line right away so that you make sure you don't cross it. Now let's go ahead and make our table. And I'm just going to start with my negative 1, 0, and 1. There are no horizontal shifts here, so I don't need to extend my input values at all. I should be sufficient with negative 1, 0, and 1. So let's plug in negative 1 first. So this will be e to the negative 1 plus 1. Minus minus becomes plus. So this is e to the first plus 1. Now just approximate here. You know that e is about 2.7, and if I add 1 to that, then this is approximately 3.7. Okay? Now let's plug in 0. So we get e to the negative 0 plus 1. Negative 0 stays 0, and e to the 0 goes to 1. So 1 plus 1 is exactly 2. Now let's plug in 1, so we get e to the negative 1 plus 1. E to the negative 1 flips us over because it has a negative exponent. So this is about 1 over e. Now think about 1 over e. E is about 2.7, or even rougher as an estimate, it's about 3. So 1 over e is approximately 1/3. So this is approximately 1/3 plus 1, or 1 1/3. You just need rough estimates here because we can't show a lot of decimal accuracy on our graph anyway. You just need to have a sense of its size. So let's plot these 3 points. We have negative 1, comma 3.7. So close to 4. 0, comma 2, and 1 1/3. So just a little bit above 1, just a little bit above that horizontal asymptote. So we have these points rising up to the left and getting smaller or decreasing as I go to the right. So it's to the right that this is going to skim that horizontal asymptote. Okay, let's take a look at e to the 3 minus 2x. Now here is another one where you might be tempted to just look at it and tell me that there is a horizontal shift by 3, either to the left or to the right. And this is where you might be wrong if you're not careful. What you need to notice before you start trying to figure out what your transformations are is that there's a coefficient in front of that x. So you're not going to get your horizontal shift correct unless you factor out that negative 2 in front of that x first. You have to do that first, otherwise you're going to be listing the wrong transformations. Now if it helps you, you can switch the order here and think of this as negative 2x plus a 3, And what we're going to factor out is that negative 2 in front of that x. Now the tricky part here is what would have to be left over. I know it has to be minus, so that a minus times a minus becomes a plus. And 2 times what will give me 3? Well, it has to be 3 halves, so that when I multiply this 2 across, the 2's will cancel, giving me just the 3 on top. So e to the 3 minus 2x is really e to the negative 2 parentheses x minus 3 halves. So initially you might have looked at this problem and said that you wanted to shift either left or right 3 units, and now over here in this factored form you'll see that that's incorrect, because if I have this minus 3 halves next to the x, that's a horizontal shift. It's going to go right because it's negative, but I'm not going right 3, I'm only going right 3 halves. And that's because we had to factor out that coefficient first before we can tell what our correct shift should be. The other transformations that I have are from this negative and also from this 2 as well. So the negative is up next to that x, so that's a horizontal reflection. So this is going to be a reflection over that y-axis again. And then the 2 on the outside is also next to that x, so that's going to be a horizontal transformation. Remember, when you multiply by a constant like this, that's either going to be a stretch or a compression. Since this number 2 is bigger than 1, we want to do, for horizontal directions, opposite of what we would expect. So instead of thinking that this is going to stretch by 2, because it's horizontal, it's actually going to be a horizontal compression by 1/2, by a factor of a half. So what that does is it takes our x's from where they normally would be and shrinks them down by half their size. And then we reflect and we shift as well. Now this is a pretty tricky one because it has a lot of different horizontal types of transformations, and anytime you're doing things horizontally, it makes your table values a bit messy. So if you want to play it safe, you can always go back to your original function. It doesn't even need to be the factored version of this. I'm just going to go back to my simpler looking function, and I'm just going to start off with my normal inputs, -1, 0, and 1. If you want to add to this, you certainly can. And I'll show you one value that we might particularly want to add. If you look at this factored version up here, one thing that I tend to always look for is that shift right. And if you were to use 3 halves in my table right here, I'm going to write it down, I would probably want to consider that value, because when x is 3 halves, that makes this power go to 0, which is a pretty important point on my graph. So sometimes I'll look for those 0 values, those x's that would make that power go to 0, and include them in my table as well. So let's go ahead and find out what some of these y values are going to be. I'm going to plug in -1 first. Be careful with your signs. So this is going to be 3, and then a -2 times a -1 becomes a +2. So this is e to the 5th. And that is probably not something that you know the value of, so you would need to go to your calculator, and you could just type in second ln, that gets you to e to the x, and I'm going to type in my 5. So e to the 5th is 148. So that's huge. This is going to be very big and way off my graph. So there's no way that I'm going to be able to actually plot that point. So we may need to extend our table a little further if these x values don't give us 3 good points. Let's go ahead and plug in 0. So if I plug in 0, 2 times 0 is 0. So this is e to the 3 minus 0, or e to the 3rd. And if I go back to my calculator and I type in e to the 3rd, that's 20. Approximately 20. Again, quite large and off my graph. So let's go to 1. Let's plug in 1. 3 minus 2 is 1, so this is just going to be e to the first, and we know that that is approximately 2.7. Now let's plug in our 3/2 value. So I'm going to plug in e to the 3 minus 2 times 3/2. The 2's will cancel, so I'll get e to the 3 minus 3, which is e to the 0, and e to the 0 is 1. So that's a nice value. Let's see if we can get one more x value that works, and I'm just going to go up to the x value 2. If I plug in 2 times 2 is 4, and 3 minus 4 is -1, and e to the -1, remember, is 1 over e, and that is approximately a third, because it's about 1 over 2.7. So we have at least these 3 points right here that are small enough that they'll fit on my grid. So I'm going to plot those 3 points. What about my horizontal asymptote? We haven't talked about that at all. Where's the horizontal asymptote going to be for this graph? Well, the only thing you need to consider are those vertical shifts. Did we have a shift up or down off to the side of this e function? No. So that means our horizontal asymptote is going to stay right at y equals 0. We're not shifting our graph up or down at all, so we're not shifting that asymptote either. So now we know where that is. We want to make sure we don't cross it, and I'm going to plot 1, 2.7, 3/2, 1, and 2, a third. And remember, we had at 0, this was all the way at 20, which would be somewhere way up here on the top of our graph. So these points are growing very rapidly as I go up into the left, like this. And then this is coming down here. And let me fix my picture here just a little bit, because I'm not supposed to hit that y-axis until way up here. So it's very steep as I go to the left there. And that's because we have that horizontal compression. We're shrinking all these x's closer together than they normally would be, so we get this really, really steep graph. Okay? Alright, now we're going to switch gears from graphing, and we're going to take a look at some common applications that surround exponential functions. And one very, very common type of application is a money formula that talks about how you can compute the amount of money in your bank account if it's earning compound interest. So a couple of variables here that we need to define. First of all, we're going to let P be our principal, and principal is the initial amount of money that you would invest into your bank account. I is going to be the interest rate per time period, so however often you're getting interest. Let's talk about how much interest you would earn after one time period. So after one time the bank computes interest on your account, how much interest would you have earned if you initially invested P dollars as principal and you're earning an interest rate of I? So how much interest would you earn after that very first time period? Well, it would just be the principal P times the interest that you're earning. Okay, so it's principal times interest. So how much money would actually be in your account? Well, remember, initially we had P dollars in our account from our principal, and now we have just earned an additional interest amount of P times I. So the amount of money in our bank account would be the initial principal P plus the interest earned, which was this PI. And what I'm going to do here is I'm going to rewrite this in a factored form. Both of these terms have a P, so let me factor out that P, and I would be left with, in parentheses, 1 plus I. Okay, now let's do this again. After 2 time periods, how much interest would we earn? Now the tricky part about this is, remember, we don't have P dollars in our account anymore. Now we have P times parentheses 1 plus I in our account because we've earned some interest already. So this is the amount of money in our account right now that's earning interest. And how much interest is all of this earning? it's earning another I%. So the interest earned would be P times 1 plus I, that's our new amount of money from the last time period, times this interest I. And if this is now our second amount of interest that we've earned, what would be the amount of money in our account? Okay, again, here it's a little bit tricky. How much did we have in our account after the first interest payment got added in? This was the amount of money in our account after the first time period. So we had initially P times 1 plus I in our account, and now we've just added another P times 1 plus I times I back into our account. So this is the new interest, and this was the original principal we had after that first amount of interest got added in. So look at these two expressions. Again, I'm going to do a little factoring here. They both have a P, and they both have that parentheses 1 plus I. So if I factor that out, then this would be gone completely and I'd have a 1 left over. This would be gone and I'd have that plus I left over. And now there's two of these, so I could rewrite this as P parentheses 1 plus I squared. So after two time periods, we have in our account P times 1 plus I quantity squared. So the amount of time periods here matches the exponent up here. So we can sort of generalize this, and we would say that the amount of money in our account after K time periods should be P parentheses 1 plus I raised to the K. Now what we're going to do is talk about compounding this interest a little bit. So compounding interest means instead of waiting an entire year to get your interest added to your account, some banks will compound your interest more frequently. So maybe a bank might compound your interest semi-annually, which means twice a year, or it might compound your interest quarterly and give you interest 4 times throughout the year, or monthly, which would be 12 times per year. So if you have an annual interest rate, so this is the annual interest rate over the entire year, but it's being compounded n times per year, then in each time period you're going to earn an interest rate I of the annual interest rate R divided by n, the number of times it's getting compounded. And how many total times per year would you get that interest? You would get it n compounding periods times the number of years that you're leaving your money in your account. So there's a lot of letters and variables here, but this is what it all comes out to be. Our amount of money, which I'm going to call A of t, so it's a function of t, is our principal P, and this is coming from this formula right here, times parentheses 1 plus I, but this time our I is going to be the annual interest rate R divided by the number of compounds per year. So I'm replacing that I with R over N. And instead of K up here, how many compounding times do I have? Well, I get N compounding periods times T years that I leave my money in there. So this is our compound interest formula. And you'll see on the next page, here it is, all typed up nice and neat. A represents the amount of money in your account after T years. P is the principal. R is the interest rate per year, and you're going to use this as a decimal. So if it said 6% interest, you'd use 0.06. N is the number of times that you're getting your interest compounded per year, and they'll tell you that in the problem. And T is the number of years you're leaving the money in the account. So we're just going to practice using this just a little bit. So number 8 here, find the value of the amount of an investment of $10,000 invested for 5 years at 6% compounded quarterly. So what do we know? We know that we're investing $10,000. So our principal is $10,000. We're investing it for 5 years. So our time, t, is 5. We're investing it at 6%, so that's your interest rate. But I want to use this as a decimal, so that would be 0.06. And it's compounded quarterly, which means we get interest added in 4 times per year. So our n, the number of compounds per year, would be 4. So we're going to use this compound interest formula, and we're just going to plug everything into the right spot. So the amount of money in our account is A. That's what we're looking to solve for. Our principal P was $10,000. And we want parentheses 1 plus R, which is 0.06, over N, which is 4, raised to the N, which is 4, times T, which is 5. And you'll need a calculator for that. So we're going to type in 10,000, whoops, parentheses 1 plus 0.06 divided by 4, parentheses, and I'm raising all of that, and you either want to multiply this in your head 4 times 5 and just type in a 20, or else use parentheses 4 times 5 so that both of those are up in the power, and hit enter, and we get 13,468. And because this is money that we're talking about, you want to round off to 2 decimal places. So this would be $13,468.55 in our account after 5 years. Okay, let's try this again. Find the present value of $10,000 invested at a rate of 8% compounded monthly for 5 years. So again, using this same formula, P times parentheses 1 plus R over N raised to the NT, our principal here is $10,000. Our interest rate for the year is 8%, which would be 0.08. We're compounding monthly, which means 12 times per year we get interest, so n is 12. And I'm going to use that n of 12 up here as well in the power, and we're doing it for 5 years. So in my calculator, we're going to type in 10,000, parentheses 1 plus 0.08 divided by 12, too many 8s there, raised to the 12 times 5, which is 60. Whoops, I must have typed it in wrong. Oh, too many little power buttons. Let's try. Jeez, this is frustrating. 60. I think I got it right now. There we go. So we get 14,898.46. Now we're going to take the same compound interest formula, and we're going to think about what would happen if instead of only being allowed to compound the interest n times per year, what if the bank allowed you to compound your interest infinitely often? Okay, so we're going to consider what happens here as n goes to infinity. That's what I mean when I say I'm going to allow those compounding periods to increase infinitely. So I'm going to let n get bigger and bigger and bigger. So instead of just compounding once a year where n is 1, or twice a year, which is semi-annually, or monthly where n is 12, we're going to let it go up to infinity. Now to figure out what's going to happen here, I'm going to do a little bit of manipulating. So look at what I'm going to do here. I'm going to leave P the way it is, and I'm going to put in some brackets here, and I'm going to take this expression 1 plus R over N, and I'm going to raise it to the N over R, and raise all of that to the R times T. Now you say, well, how can you do that? Well, look at what happens right here. This stuff is being raised to a power to a power. So according to our laws of exponents, these two powers need to multiply together. And what happens when you multiply n over r times rt? The r's would cancel each other out, giving you just the n and the t back again, which is exactly what the original formula had. So all I did was a clever way of breaking this up so that it's in a slightly different form, but still equivalent to what I started with. And now what I'm going to do is I'm going to create a new variable, and I'm going to call it m, and I'm going to let this m represent this fraction n over r, this power right here. This is going to turn into my m. So notice a couple of things here. If m is n over r, then what is r over n? Well, it's the reciprocal of m, so it would be 1 over m, correct? Also notice that if n goes to infinity, if this numerator gets bigger and bigger and bigger, and this denominator r is a fixed constant, a fixed interest rate, if n is getting really big, but r is staying fixed, then what's happening to m? Well, if n is getting big, then so must m as well. So if n is going to infinity, then so is m also going to infinity. So let's see what this turns into. Let me do a little substitution of variables. The p stays p, and then in the parentheses here we get 1 plus, and instead of r over n, remember r over n was 1 over m, the reciprocal of m. And this n over r was my m, and all of this was being raised to the rt. Now look at this expression right here. This goes back, let me scroll back up several pages to something we talked about earlier. Anytime you have an expression that's of the form 1 plus 1 over your variable raised to a variable, where that variable is going to infinity, that approaches e. So instead of using n's here, I'm using m's. 1 plus 1 over m raised to the m, as m goes to infinity, is going to turn into e. So in other words, back here in my problem, this expression right here, 1 plus 1 over m raised to the m, as m goes to infinity, this approaches e. So all of this right here becomes an e. So my formula becomes p e to the rt. Sometimes you hear this called PERT. So this is going to be called the compounding continuously interest formula, PERT, where the A is the amount of money in your account, P is our principal, R is the interest rate as a decimal, and T is time. So if you go to a bank and they let you compound your interest continuously, that's the word or phrase that is going to give away this formula. Anytime you see this word continuously, then you're going to be wanting to use the PERT formula. So if you're getting compounded interest continuously, then it's going to be determined by this PERT formula. So for example, find the amount of money if $1,000 was invested at 11% compounded continuously for 1 year. So it doesn't tell me a specific number of compounds that I'm supposed to use. It has that word continuously. So that's how I know that I'm supposed to use PERT. And let's plug in what we want to know. We're trying to find the amount, so we're going to try and find A. The principal is this $1,000. My base is E because we're compounding continuously. My R is this interest rate 11% as a decimal, so 0.11. And I'm putting it in for 1 year, so it's 0.11 times 1. So we would go to our calculator and type in 1,000. And then we're going to do e to the x, and inside those parentheses I'm doing that 0.11 times 1. So I get $1,116.28. Okay? All right. Switching gears to another common type of application problem involving exponential functions is population growth. Population growth can be modeled with the exponential formula P of t equals P sub 0 of e to the RT. So this looks very similar to that PERT formula because you have that P e to the RT. P sub 0 is your initial population. So instead of your initial investment, in this scenario, now it's your initial population. Your interest rate, R, is now going to be called your growth rate, so how much this population grows, and you want to use it as a decimal. T is time, and P of t is the population at any time t. So it's very, very similar to that compounding continuously formula. So it's just like PERT. So we're going to use that in this example. The population of a city was 250,000 and is growing at a relative rate of about 5% a year. What would you expect the population to be in 10 years? So whenever you see exponential population growth, you're going to assume that it follows this model. P of t, or the population at any time t, is P of 0, the initial population, times e to the RT. We're trying to find out what the population is in 10 years. So when our time t is 10, we know that the population of the city initially was 250,000, so our P sub 0 is 250,000, and it's growing at a relative growth rate at 5% per year. So our R as a decimal would be 0.05. So we're trying to find P of 0, which is 250,000, times e to the R, which is this 0.05, times t, which is 10 years, and what this is finding for us is the population at 10 years. So we need to type in all of this into our calculator. So we want 250,000 E, I think I have too many zeros there again. E to the 0.05 times 10. And we get 412,180, and I'm just going to round this off to the nearest ones place because these are people that we're talking about. So this is 412,180. So in about 10 years, my population has almost doubled, not quite. Okay? Now this is population growth, assuming an exponential model. However, in real life, population doesn't usually grow exponentially because there's other factors like resources that can affect how fast or how much a population should grow. So a more realistic model for population growth is called logistic growth, and it has a very complicated looking formula that's a over b plus ce to the negative kt. So this is a complicated looking type of model, but it's more realistic because it takes into considerations things like how much food you have, if there's predators and prey, what kind of supply and demand there is, and things like that. So let's see an example using logistic growth. So we have a population of a certain species of bird, and it's limited by the type of habitat required for nesting. The population is modeled by this logistic growth formula. So it's giving you this population formula already. You don't need to come up with it on your own. What is the initial population? So initial population is going to be at time 0. So whenever you see that word initial, that's assuming time 0. So we're trying to figure out what is this population function when t is 0. So let's plug it in. 5600 over 0.5 plus 27.5 e to the negative 0.044 times 0. Now if we go to simplify that, this negative 0.044 times 0 all becomes a big fat 0, and e to the 0 goes to 1. So in the denominator, we're just going to get 0.5 plus 27.5 times 1, which is 5600 divided by 28, and that is 200. So what did we just find out? What were we talking about here? This was population of a species of bird. So at time 0, or the initial population, is that I start off with 200 birds. And then probably because of the type of location that these birds live in, there's maybe only a certain number of trees that can allow these birds to nest, or wherever they particularly live. Because of the resources, there may be, a point where if there's too many birds, then there's not enough places for nests. So this could limit the size of our population, which is what this logistic growth formula is going to tell us. So that's what we're going to try to figure out in part B. What is the limiting value? Which really just means what happens to this population as time progresses. Where is this population of birds going to level off at because of the resources that are available to it? If it gets too high, then the birds will start dying because there won't be enough room for their nesting. And if it's too low, then they have space to keep growing and increasing their population size. So where's the happy medium? Where do they sort of level off at? So to figure this out, to find this limiting value, what we're going to do is we're going to find out what happens in the long run, because that's what's going to be this limiting value. What happens in the long run as this population stabilizes? And in the long run, that means time is getting infinite. So if I could let time continue to pass and pass and pass, as time goes to infinity, what is this population going to stabilize at? So what we're really trying to do is figure out what this population does as t gets bigger and bigger and bigger. So what we're going to have to do is imagine plugging in infinity right where that t is. But you can't really plug in infinity, right? Because it's not a number. But we're going to put it in there just so that we can kind of visualize what we're really trying to consider. Now think about this for a moment. What do we have right here? We have e to the negative 0.044 times infinity. Well, 0.044 times something huge is going to stay huge, but there's a negative in it. So we need to figure out what e to the minus something big does. We need to figure out what e to the negative infinity does. So there's several ways to think about this, but hopefully by now, after our talk about graphing, you should have a basic idea of what the graph of e to the x looks like in your head. The base e is about 2.7, so that's bigger than 1. So this is an exponential growth graph. So it's going to have a shape that looks like this. Now we want to look at e to the minus infinity. So we want this x to be minus infinity. So what happens on this graph as x goes to minus infinity? Well, minus infinity would be this way. What are these e to the x values doing? That's where they're asymptotic. So e to the minus infinity is getting closer and closer to that 0. So that means that all of this is going to 0. So in terms of our formula, this would become 5600 over 0.5 plus 27.5 times 0 is going to stay 0. So this is 5600 divided by 0.5, which becomes 11,200. So in the long run, this bird population will stabilize at 11,200 birds. Any more than that, and there won't be enough resources for these birds to survive, and they'll start dying off. Any less than that, and there will be enough resources that they could continue to grow. Okay, to finish off here, let's just take a peek at the graph of this logistic growth formula. And it's too complicated to graph by hand, so you're going to have to look at your calculator to do that. And I think that I've already typed it into my y equals just to save some time. And instead of t, I had to use x, so this is 5,600 divided by parentheses 0.5 plus 27.5 e to the negative 0.044x. And if you just do a standard window to begin with, you're not going to see anything. Because remember what our initial population was? Our initial population of birds was 200 birds. And this is a window that's negative 10 to 10 for both x's and y's. We also saw that the limiting value of this population was 11,200. So our population is going to get as big as 11,000. And in our function that we typed into our y equals, the population is this y value. So we need our y's to be at least as big as 11,200, otherwise we're not going to see anything. So let's adjust our window. I'm going to let x go fairly large so we can see the long run. Remember, we were looking at t going to infinity. So let's let our x's get fairly large as well. And we only need to consider positive time. So I'm going to let my x min be 0. And I'm going to let my x max be, let's just say 500. And I'll let my x scale be 100. And for my y's, whoops, it jumped on me. Sorry about that. Let's go back and adjust our y's. I'm going to let my y min start at 0 as well, because we don't really need to consider negative populations here. And because our highest population is at about 11,200 from our limiting value, let's let our y max be slightly bigger than that so we can see this, maybe 12,000. And our y scale can be maybe 1,000. Hit graph. And this is the typical shape of logistic growth. It almost looks like an S shape. You have that initial exponential growth at the beginning when there's so few birds and so many resources that this population can grow really, really quickly. But then resources start to decline and that population will level out. So this approaches a horizontal asymptote right up here at that height of 11,200. And if the population were to go above that, then the birds are going to start dying off. So it levels off at that limiting value. So this is the typical shape that you'll always see whenever you have logistic growth. So I'm just going to copy that shape down here in my notes. So it's going to have this sort of S shape to it, where this levels out right at that 11,200. Okay, that concludes our lecture on exponential functions. Good luck.